Welcome to Course 101, TiDB Technical Essentials. This is Module 3, TiKV. My name is Jeff and I'm your instructor for this module. Once you complete this module, you will be able to understand the architecture and role of TiKV, understand TiKV data persistence and reads, understand how TiKV provides MVCC and distributed transaction support, understand the distributed consistency of TiKV based on the Raft algorithm, and finally, understand TiKV's coprocessor. In the previous module, we learned that TiDB server is a stateless SQL layer that exposes the connection endpoints of the MySQL protocol to the outside world. SQL processing is not very useful without storage. That's where TiKV comes in. The core function of TiKV is data persistence. TiKV stores OLTP data in the TiDB database. This capability is implemented by an embedded RocksDB server. TiDB is a distributed storage engine. The data is spread out into regions. The Raft consensus algorithm is used to ensure strong consistency of data in this distributed environment. Each region and its replicas form a Raft group, and the combination of multiple Raft groups is called multi-Raft. We will introduce replication and leader election in Raft, as well as data writing, reading, splitting, and merging based on the Raft consensus algorithm. Later, we will introduce the TiKV coprocessor capability. This provides TiDB with the ability to execute select operations that are pushed down from TiDB server. We can use this function component to hand over some SQL calculations such as filtering, aggregation, projection to TiKV to complete. There is no need to return all the data in TiKV to the TiDB server via the network, nor is it necessary for the TiDB server to do all the query processing. This saves network bandwidth and CPU load on the TiDB server. Plus, and this is important, the coprocessor allows TiDB to distribute processing across multiple TiKV nodes. RocksDB is a persistent embedded key value store. RocksDB is optimized for flash storage with minimal latency and uses log structured merge trees or LSM trees for storage. So let's talk about some of the characteristics. It is a high performance key value database. Its perfect durability mechanism while guaranteeing performance and safety, good support for range queries. It's designed for application servers that need to store terabytes of data to local flash or RAM, and it's optimized for small and medium key values stored on high-speed devices. Once again, can be stored in flash or directly in memory. Finally, performance increases linearly with the number of CPUs, making it friendly to multi-core systems. Let's look at how RocksDB writes data. RocksDB uses the data structure of the LSM tree to store key value data, and LSM tree will insert, modify, delete all data stored in memory, and when such operations reach a certain amount of data, it's written to disk in batch. When writing to disk, the previous data will be merged. During the merge process, the original data is not modified like a B+ tree. New data is inserted directly, thus avoiding random writes. The structure of the LSM tree spans memory and disk and contains several parts such as mem table, immutable mem table, and SST table. We explain the workflow of the LSM tree and its related components with a single write operation in the figure. First, we back up to disk via write-ahead logging, or WAL, to prevent data loss. WAL is a series of techniques used in relational database systems to provide atomicity and persistence. These are two of the ACID properties. On systems that use write-ahead logging, all modifications to the data must be written to the log file before they are committed to the database. Once write-ahead logging is complete, data is written to memtable. Memtable is an in-memory data structure that stores the data before it is written to disk. Memtable can use data structures such as skip lists or search trees to organize data and maintain order. Memtable services both reads and writes. New writes always insert data into memtable, and read operations always query memtable before querying the RocksDB sorted string table or SST file. Because the data in memtable is always up to date. Let me repeat that. The data in memtable is always up to date. When memtable reaches a pre-specified size, memtable is converted to an immutable memtable. The immutable memtable is a memory-based data structure that cannot be modified. Once again, immutable memtable cannot be modified. During this process, the memtable is transformed into an intermediate form of an SST. The goal is to not block writes during the staging process. Writes can be processed by the new memtable without waiting for a lock. A new memtable is created to handle the new data. A background thread will drop the contents of this memtable into an SST file as a collection of ordered key value pairs, which is the structure of data in the LSM tree on disk. The data in memtable will eventually be converted to an SST and saved to disk. Once this process completes, the existing memtable is destroyed and the write-ahead log file containing the data related to the new memtable can be deleted. Next, we will focus on the way RocksDB files are organized. Files on the disk are organized in multiple layers. Let's call them level 1, level 2, etc. A special layer, level 0 or L0, will contain data that has just been dropped from memory memtable. Each layer, except level 0, is an independent sort results. At each layer, except level 0, the data is split into multiple SST files. The keys in each SST file are in sorted order. If we need to locate a key, we first find the start and end keys of the files in two parts. We locate which file has this key and access the location in the file. In general, it's a binary search of all keys in that layer. The goal of compression is to limit of these layers. The data size will trigger compaction to the next layer, and the size goal is usually an exponential increase of the previous layer. For write-ahead logs, WAL serializes memtable operations and stores them in log files on the permanent media. In the event of a crash, the write-ahead log file can be used to rebuild the memtable to help recover the database to a consistent state. When a memtable is safely placed on persistent media, the associated WAL log or write-ahead log becomes out of date and then archived. The final archived logs are deleted from the hard drive after a specified time period. At this point, the data has been persisted. We can see that the write-ahead log guarantees that writes will not be lost. Next, let's cover delete operations. When there's a delete operation, it's not necessary to find the corresponding data on disk like a B+ tree and delete it. You only need to insert a piece of data into memtable as a flag, such as delete key 1233. That's an example. When the read operation reads this flag in memtable, it will know that the key has been deleted. Then, in log merging, the data marked for deletion will be deleted during the merge process. The update operation is similar to the delete operation. Update only operates on the memtable. It writes a flag, and then the actual update operation is delayed and completed at the time of merge. And random writes will be changed to a sequential write. Since the data is stored in RocksDB, the queries must be completed through RocksDB. First, let's understand the RocksDB query operation. The query operation needs to read memtable, immutable memtable, and then disk, which is really SST files. And that's SST tables 0, SST table 1, you get the picture. You need to iterate through all the collections in reverse order. In this example, it is important to note that if one piece of data does not exist in all data sets, the search will be repeated in vain. Fortunately, RocksDB uses Bloom filters to speed up read operations. When the Bloom filter determines that there is no data to read in the corresponding SS table, the SS table is skipped. RocksDB also has a block cache function. We can set a space in memory for the block cache. This cache contains data that we access often, so the query operation will prefer to read data from the block cache. If the data is not in the block cache, then it uses memtable read process described in the diagram. We have seen that TiKV integrates RocksDB for basic data persistence. Next, we will look at another feature of RocksDB, column families. A column family is a database object that contains columns of related data. TiKV uses column families for transaction support. Support for column families began in RocksDB 3.0. Each RocksDB key value pair corresponds to a unique column family. If a column family is not specified, the key value pair will correspond to the default column family, which is also the default column family for the RocksDB instance. Column families provide a way to logically fragment a database. Some of its features include support for cross-column atomic writing, consistent view across column families, allows different configurations for different column families, and add, remove column family instantly. Both operations are very fast. Another thing we need to note is that the main implementation idea of the column family is that they share a write-ahead log, but they do not share a mem table and table files. Atomic writing is achieved by sharing write-ahead logs. By isolating mem table and table files, we can configure each column family independently and quickly delete them. We can only delete this write-ahead log file if all column families have been flushed. This ensures that all your column families will be flushed regularly. At this point, we've introduced column families. We know that RocksDB instances can have multiple column families. Each column family corresponds to a key value pair, and each column family has a mem table and table files of their own. But column families share a write-ahead log.